ሰላም ጤና ይስጥልኝ የተወደዳችሁ ተማሪዎች እንዲሁም ወላጆች ሰላምታ ይበያላችሁበት ይድረሳችሁ በአገራችንም በሎም በአለም በተከሰተው ወረርሽኝ ምክንያት ያደረሰ ያለውን ጉዳት እንረዳለን ስለዚህ ራሳችሁን እንድትጠብቁ ለማሳሰብ እወዳለሁ ስለዚህ ወደ ሌሰናችን ስንመለስ on our previous discussion we have tried to define what magnetism and magnet is. We have also tried to classify substance into three, depending on the property they show when they are exposed to external magnetic field, as paramagnetic, diamagnetic, and ferromagnetic material. So, and we have also tried to see, at last, we have also tried to see a very important point when a charged body, around a charged body, there is electric field. The same is true that there is a magnetic field around a moving charged body, And there is also, if a charged body is immersed into a uniform electric field, there will be a force exerted on it. So the point that we have discussed here is a point. Around any charged body, there is electric field. Around any charged body, there is electric field, and that electric field can be determined as K, Q over R squared. This was the concept of electrostatics. And the other point, in magnetism, the same expression is found. Around a moving charged body, it's possible to determine magnetic field. Let's take it here. If there is a point charge, around this point charge, there is electric field, E. But if this charged body is in a state of motion, there is a magnetic field. Suppose this charged body is moving with speed V, in this direction, velocity V. So to determine the magnetic field at a point R, let's take it to be R here, at this point we can have magnetic field B. So from any point charge, there is an electric field. It's possible to find the electric field. And around any moving charged body, there is magnetic field. This was our previous discussion. It's possible to find electric field E as KQ over R squared. And the other point, it's possible to determine magnetic field as the permeability of free space over 4 pi and the charge Q, this is the charge, and there is a velocity V cross the normal line to the displacement. Here we have a distance or displacement, therefore it's possible to have a unit vector. So cross the unit vector R over R squared. This is how we determine a magnetic field around a moving charged body. And the other point that we have discussed is, if a charged body is immersed into a uniform electric field, the electric field will exert electric force. Suppose here we have a uniform electric field which is acting to the right. Suppose if a point positive charge is immersed into this uniform electric field E, there will be electric force exerted on the charged body. And the direction of the electric force is along the field. It's possible to find the electric force. It's a vector quantity. We already knew this. And F can be given as electric field E times Q. And electric field strength is also a vector quantity. The direction of the force is along the field for a point positive charge. Whereas for a point negative charge, the direction of the force is opposite to the field. The direction of the force and the direction of the field are opposite for negative point charge. The same expression appears for a charged body, a moving charged body immersed into a uniform magnetic field. And it's possible to have a different direction. For example, the magnetic field might act to the right, to the left, upward, or downward. We have also a very important direction in physics to point magnetic field. Suppose if a magnetic field is moving into the page, if the magnetic field is moving into the page, meaning on your textbook or any books, the magnetic field might move from you towards the page, therefore into the page. To point represent into the page, it's possible to use cross. So whenever we use cross from this time on, showing that magnetic field is acting into the page, And whenever we use dot, if you use dot, we are saying that the magnetic field is moving towards you, out of the page. In this case, out of the screen, okay, into the page, and in this case, it's possible to use out of the page. It's possible to use dot and cross. Therefore, if we take a magnetic field which is acting into the page, suppose here we have a magnetic field which is acting into the page. And if you have a point positive charge which is moving to the right, let's take a positive point charge which is moving to the right. The speed or the velocity, let's say the velocity of the charged body is to the right, and the direction of the magnetic field is towards the page or into the page. Then how do we determine the force? Well, the force mathematically expressed as F equals to, vectorially represented as F equals to Q, the charge Q, the velocity V cross magnetic field B. This was what we have seen previously. So today, let's try to determine this magnetic force using right-hand rule. It's possible to determine its magnitude using this mathematical expression as F equals to Q V B sine theta. It's possible to find the magnitude of the force. How do we determine the direction? Well, from cross vectors, you already knew that the resultant vector is always perpendicular to those vectors. Therefore, in this case, we are just saying that the force F is always perpendicular to both the velocity V and the magnetic field B. So let's try to see it here. Now let's use right-hand rule. We have different right-hand rules, actually, but the most common is using those three fingers. Those three fingers, index fingers, the middle finger, and the thumb. So you have to point your index finger to the direction of speed or velocity. Your middle finger must point to the direction of magnetic field. And your thumb always points to the direction of the force. So it's possible to use this one. It's possible to use your palm. For example, it's possible to indicate your forefingers to the direction of the velocity. Then your palm points to the direction of magnetic field. And your thumb, after all, represents the force. There are different ways to represent right-hand rule, but the most common is to use those three fingers. So in this case, our index finger points to the direction of velocity, our middle finger points to the direction of magnetic field, and our thumb points to the direction of the force. This is the direction of the force, which is the cross product of the velocity and the magnetic field. This is the force. So let's try to use our right-hand rule and find the direction of magnetic force. Previously, I have mentioned that whenever you use cross, it means that your magnetic field or something is pointing into the page. Dot means out of the page. Students, can you try to determine the force now if a positive point charge is moving to the right, and the direction of the magnetic field is acting into the page? In this case, right-hand rule is always used for a positive point charge and for an electric current for a conventional current flow. Okay, it's possible to use left-hand rule actually for negative charge, but I recommend to use right-hand rule and invert for negative charge. Okay, therefore, in this case, let's try to see about how to use right-hand rule for a positive point charges. Suppose here we have a positive point charge and it's moving to the right, to the right. And the direction of the magnetic field is from you towards the page, into the page. Okay? Therefore, what is the direction of the force? Well, first you have to point your index finger to the direction of velocity. And your thumb, your middle finger must indicate to the direction of what? The magnetic field. Magnetic field is into the page, into the page. So here you have the velocity, the magnetic field. Your thumb is pointing to the direction of upward, so that the force exerted on this charged body is upward. What do you mean by upward? Well, this charged body is starting to move upward gradually. Okay? If this charged body is negative, it's possible to use left hand rule, but I wouldn't recommend to use that. You have to use right hand rule. Right hand rule and invert the result of every negative and electron current. For practical situations, actually, it's possible to use that. So again, if the negative charged particle, like electron, is moving with a speed v or velocity v in this direction, and the magnetic field is acting into the page, so you have to point your index finger to the direction of the velocity. The magnetic field is still acting into the page, so your force indicates upward. But it doesn't mean upward, because it's negative charge. Therefore, the result is downward. So the force exerted on the negative charge is downward. That means the charged body is moving gradually downward. So now again, let's try to take, there is a magnetic field which is acting out of the page, So if a positive charge is moving again to the right, you have to point your index finger to the direction of velocity of the charged body. So in this case, your middle finger must point to the direction of the magnetic field, but the magnetic field is pointing towards you, out. So you have to invert this out, like this, out. So your thumb points to the direction of the force. Therefore, the force exerted on this charged body is downward. There is a magnetic field which is acting out of the page. The charged body is moving in this direction. Therefore, the velocity, the magnetic field is out of the page, and the force is acting downward. So the force exerted on this positive point charge is acting downward. If this charge is negative, like this, what is the direction of the force, the magnetic force? Well, the direction of the magnetic force, again, you have to point your index finger to the direction of the velocity, and the direction of the magnetic field is not into the page, it is out of the page, So when you point your thumb, it's indicating downward, but it doesn't mean downward. Why? Because the charge is negative, so you have to invert it upward. So take care and try to identify which charges are in these situations. Now let's proceed. Suppose here we have a charged particle of 4 microcoulomb, positive charge particle, 4 microcoulomb, is moving with a velocity of 120 meters per second along a positive x direction. And it is immersed into a uniform magnetic field of 10 millitesla. And the magnetic field is acting in the positive y direction. So what is the magnitude and direction of the magnetic force? Students, I want you to try that, please. Students, I hope you have tried that. So let's try to solve it together. So what are the given quantities? The given quantities are the charge. Here we have the charge. The charge is 4 microcoulomb. And the other variable or quantity given is the velocity of the charged particle and its direction as well, in the positive x direction. And it is immersed into a uniform magnetic field, which is 10 millitesla. Now the question is, what is the magnitude and direction of the magnetic force? The magnetic force. So what are the given quantities? Given. The charge is given. Sorry. The given variables, charge is given to be 4 microcoulomb, which is 4 micro means 10 to the power of minus 6 coulomb. And the velocity of the charged particle is given to be v equals to 120 meter per second to the direction of a positive x-axis. It's moving to the positive x-axis. What is the direction of the magnetic field? The magnetic field is acting upwards to the direction of a positive y-axis. So magnetic field B is given already here, 10 millitesla. By the way, the SI unit of magnetic field is Tesla. We have already mentioned that it was given in honor of Nikola Tesla. So 10 millitesla can be equivalently represented as 10 times 10 to the power of minus 3 Tesla. Therefore, we are asked to find the force, the magnetic force. What is the direction and the magnitude and direction of the force? That is the question. So, solution. Force can be given as B, the magnetic field B, V, velocity V, Q, sine theta. Where in this case, theta is the angle between the velocity and the magnetic field. So what is the direction? What is the angle? Theta. In this case, the angle is 90 degrees because this is the velocity V and this is the magnetic field B. So the angle between the magnetic field and the force is the speed, the velocity V is 90 degrees. So theta is 90. Theta is 90 degrees. So when we substitute all these variables, F can be given as what? B is already given to be 10 milli means 10 to the power of minus 3. The velocity V is 120 and the charge is 4 times 10 to the power of minus 6. In this case, we have already written as sine 90 degree. Okay? If this charged particle has other angle like 30, 60 and so on, it's possible to substitute. For example, if this charged body is moving like this, okay? If the speed or velocity or the motion of the charged particle is in this direction, there is an angle theta. So you have to put that angle. In this case, it's 90, so sine 90 is 1. Sine 90 is 1. So we can determine the magnetic force as, here we have the solution, 4.8 times 10 to the power of minus 6 Newton. Minus 6 Newton. So I hope you have found this answer. What is the direction of the force? This is the magnitude. What is the direction of the force? Now you have to use your right hand rule. So the right hand rule states that first you have to point your index finger to the direction of velocity. Then your middle finger to the direction of magnetic field. So your thumb always points to the direction of the magnetic force. So in this case, we have the speed, and the speed is to the direction of, we have the velocity to the direction of a positive x-axis. Positive x-axis. The magnetic field is acting upward. So what must you have to do? You have to invert. You have to rotate your finger like this. The speed, the magnetic field is upward, and the magnetic force is out of the page, towards you, out of the page. Okay? So the direction of the magnetic field, the magnetic force is out of the page, and out of the page can be represented using a dot. Out of the page. What's the meaning? What's the meaning of out of the page means? Well, the direction of this charged particle is moving towards you. That means the charge which is moving in this direction, when it is immersed into this magnetic field, it starts to bend and move towards you, out of the page. So I hope you have found this answer. Now let's proceed. Students, the other concepts that we should have to discuss is all about magnetic flux. Magnetic flux is a very important term. In electric flux, we have also a magnetic gravitational flux. Usually, whenever there is a field, there is flux. So, previously in Unit 4, I hope you have tried to see electric flux, phi. It is a scalar quantity which measures the number of electric field lines, or the number of magnetic field lines, or the number of gravitational field lines which penetrates a given cross-sectional area. Therefore, in this case, we are trying to see magnetic flux. Magnetic flux. There is a source, a magnetic source, and that source will produce magnetic field, and magnetic field is represented using magnetic field lines, and those field lines would penetrate a given cross-sectional area. So, mathematically, it can be represented using this. Let's take it here. For example, you have a magnetic field, or a magnet here, south pole of a magnet, so the magnetic field lines are running into this. Suppose if you have a cross-sectional area A, in this case, the number of magnetic field lines which penetrate this given cross-sectional area is termed or measured using flux phi. This is a Greek letter, phi, 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 or phi. So flux phi is given as B, which is magnetic field, dotted with area A. Area A. This is how we determine magnetic flux. The same concept was up here in electric flux. We have stated that flux phi in electric field is electric field strength dotted with area A. Area A. Students, in this case, we have seen that magnetic field is a vector quantity. Is area a vector quantity? Because that the dot product means resultant of scalar, because of that both are vectors. Is area vector? Is area vector? Well, area is actually vector due to its normal line. Area is not a vector quantity, but due to the normal line. The normal line means the perpendicular line on the cross-sectional area, we can consider it as a pseudo vector, false vector means. Therefore, it's possible to use this. Let's back again. B dotted A. B dotted A. The magnitude of magnetic flux can be determined as what? B, which is magnetic field, A, cross-sectional area A, cosine of theta here, theta. Where theta is the angle between the magnetic field and not the area, rather the normal line or the perpendicular line to the area, And sometimes some books represent this as flux phi can be given as what? Magnetic field B dotted with N, normal line. They are making the normal line as a vector times area. It's possible to use that. And sometimes in some books use sine, and sometimes commonly use cos. Cos tells us that the angle theta, this angle theta, is always the angle between the magnetic field and what? The normal line. So when you proceed here, for example, here you have area, cross-sectional area, and you have a magnetic field B. Or in this case, you have a cross-sectional area like this, and the normal line, a line which is perpendicular to the area. Here we have the normal line, the normal line. The magnitude is 1, but it indicates the direction. For example, the normal line indicates to the positive x-axis. In this case, it indicates to the direction of a positive y-axis, the normal line. So, for example, let's take here. The magnetic field is moving to the direction of a positive x-axis. The area is perpendicular to the magnetic field, The magnetic field is acting in this direction, and the area is in this direction, so they are mutually perpendicular. But we are not going to take theta to be 90, because we are trying to find theta or express theta as the angle between the magnetic flux, the magnetic field, and the normal line. So theta should be taken as what? 0, even though the area is perpendicular to what? To the magnetic field. Area is perpendicular to the magnetic field. So what is theta? Theta is not 90, because we are going to take theta to be the angle between the normal line and the magnetic field. So theta becomes 90. In some books they use sine, because they are just taking directly area perpendicular to magnetic field as 90 degree. At that moment they might use theta to be 90, be a sine. They might use sine. In this case, sine means the angle between the area and the magnetic field. But usually in physics, in standard physics books, they use cos, and at that moment think that the angle is between the magnetic field and the normal line. So students, can you try what is the angle here? As the area is parallel to the field, area is what? Parallel to the magnetic field B, Is theta 0? If you use flux phi is equals to B A cosine of theta. What is theta? Well, theta is the angle between the magnetic field and not area. What is that? The normal line. If you use 0, for example, area is parallel to the magnetic field, meaning the normal line, the line which is perpendicular, in this case, is acting upward. So the normal line and the magnetic field are perpendicular. So normal line is perpendicular to the magnetic field B, so theta becomes 90. So in this case, there is no magnetic field which penetrates this given cross-sectional area. The magnetic flux is 0, because when you substitute as cos 90, it gives us 0. Okay? So I want you to try those concepts, read those concepts. Now let's try to determine its unit. What is the unit of magnetic flux? The unit of magnetic flux can be given as the unit of magnetic field and the unit of cross-sectional area. The unit of magnetic flux is Tesla, as we have already previously mentioned. The unit of area is meter squared. So what is the SI unit of magnetic flux? The SI unit of magnetic flux is Weber, actually in honor of William Edward Weber. Okay, so 1 Weber can be represented as 1 Weber. In this case, 1 Weber is equivalent to that of what? 1 Tesla meter square. Previously, we have defined Tesla to be 1 Tesla is equals to 1 Newton second over Coulomb meter. The other point is Newton over Coulomb per second can be rearranged and gives us ampere. So the SI unit of magnetic flux is Tesla, and Tesla can be equivalently represented as Newton meter ampere or Newton second Coulomb meter. Okay? And it's also possible to rearrange and find that 1 Tesla is equivalently equals to Weber per meter square. So this expression, this expression and this expression are all gives us Tesla. Now let's proceed and try to see the motion of charged particles in a uniform field, in a mixed field or in a combined field. There is a uniform electric field and there is a uniform magnetic field. And the combination of these two gives us a very, very important application in our day-to-day life. And the most common electrical components use this mixed field or combined field. Combined or mixed field means the combination of both electric and magnetic field, and electric field and magnetic field. the most common important device which use mixed field are velocity selector, J.J. Thomson's apparatus, and mass spectrometer. These are the most common and very important electrical components. So first let's try to see what does it mean by mixed field. Mixed field means a combination of electric field and magnetic field. Suppose this is a velocity selector. This is the concept of velocity selector. Let's take two parallel plates like this, a positive and a negative plates. So whenever there are two plates in electrostatics, you have learned that electric field runs from positive to the negative. Therefore, from this to this downward, electric field lines runs from positive to the negative. Let's take two parallel plates. Those plates are positive and negative. Positive and negative. So electric field lines runs from positive terminal to the negative terminal. Now let us take a magnetic field which is acting into the page. Meaning from you towards me. So the magnetic field are acting into the page like this. Into the page. So the magnetic field B here is acting into the page and the electric field is acting downward. Suppose a positive point charge is launched perpendicularly in this direction to the right. A positive point charge. It's possible to use a negative as well. But in this case, let us take a positive point charge. Is moving with a velocity v and immersed into this mixed field. This mixed field. What would happen to this charge? Well, the force, the electric force, tend to move this charged particle downward, the electric force. When we take only the electric force is acting downward. So when this charged particle is moving, we have stated that electric force is acting along the field. The direction of the field is downward, and the direction of the force must be acting downward as well. Because in electrostatics, the direction of the force and the field are the same for positive point charge. So it tends to act on this positive point charge and tries to move it downward. Whereas the magnetic field, let's take only the magnetic field is acting into the page. If it was only magnetic field, as the point charged particle is moving, or the velocity is to the right, and the magnetic field is into the page. So your thumb points upward. So the direction of the magnetic field is upward. It tends to move this charged particle upward. So in this case, the mixing or the combination of these two, on this charged particle, there is a force which is acting upward, and that force is due to the magnetic field. And there is a force which is acting downward due to the electric field. Okay? So if the magnetic field is more or greater than the electric field, it tends to move upward. If the electric field is larger than the magnetic field, it tends to move downward. So the velocity selector is a device which used to determine the velocity of different particles. How do we do that? So let's try to find it here. Look at here. If a given charged particle is moving with a speed v, the magnetic field exerts a force. This is the magnetic force acting upward. And here we have electric force, which is acting downward. So what are we going to do? Either we increase the field upward or downward. We are increasing the magnetic field so that this line is moving, this charged body is moving straight. Okay? So we'll try to see mathematical expression of and try to determine mathematical expression of velocity next time. So students, I want you to try and find this. So see you then.